In this video, we're going to continue our discussion of thermochemistry or thermodynamics for a general chemistry audience. And we're going to look at how entropy changes during changes in temperature, volume, and pressure. First thing we're going to look at is we're going to look at volume changes, and we're going to start from the first law of thermodynamics. So recall the first law of thermodynamics, which says that the change in total internal energy is the sum of heat and work. Where U is the total internal energy, Q is heat, W is work. We can solve for heat. So we can say that heat is the change in total internal energy minus work. So we just take work to the other side, we transpose work. And now we're going to divide through by temperature. So we're going to divide through by temperature. So we get heat over temperature in Kelvin is change in total internal energy by temperature minus work over change in temperature. And we state that the change in heat per unit temperature, this is the change in entropy of the system. So let's actually phrase this and we'll give it a number. So we'll say that the change or the ratio between heat and temperature is an entropy change. You might wonder, how come there's a change on the right but there's no change on the left? You can put a change if you like. So I'm assuming that heat here is the same as a change in heat. Remember that heat is a path function, so it gives a non-definite integral. So we can represent that, a non-definite differential, sorry. So we can represent that by a line through the D. So most people don't write dq, they just write q, but it can mean dq as well. So if it makes you feel better, you can put a D here. Okay, so let's give this a number. I don't know, let's call it equation 1. So I'm going to call this equation 1. So Q, or dq by T, is ds. Let's call that equation 1. Now let's impose some conditions. So let's say under isothermal conditions, so isothermal, iso means same, thermal means temperature. So under constant temperature conditions, then we can state that the change in total internal energy is 0. So this is a statement going back to our discussion on heat capacities. And recall from our first law of thermodynamics that if du is 0, then the sum of Q plus W is also 0. So this means that a positive heat is equal to a negative work, and vice versa. A positive work is equal to a negative heat. So let work, remember from a previous video, looking at isothermal, looking at constant pressure work versus varying pressure work. So under varying pressure work, by definition, work is minus nRT log final volume over initial volume. So just to restate this equation here, so again, this is work under variable pressure conditions. So you can look back at a previous video on that. So work is this here. So I want to take the negative work, so I would just go ahead and change the sign on all of this. So if positive work is negative this material, then negative work would be positive that material. And that's equal to positive heat. So I've got this statement here. Again, under isothermal conditions, change in total internal energy is 0. That's the sum of heat and work. So if the sum of heat and work is 0, I can transpose work over the other side. So a positive heat is equal to a negative work. Going back to a work equation for reversible, for variable pressure. So when the work done against, for example, when a gas expands, when the pressure at which the gas is expanding into is changing, then we have this work equation. We can set it to negative work, which is also equal to positive heat. So we have an equation now set equal to heat. Okay, I'm going to pause the video, tidy up the board, and we're going to continue from this equation here. Okay, so picking up where we left off, on the previous board we had this equation here under isothermal conditions. So we've got heat is moles, ideal gas constant temperature, multiplied by the log of the ratio of the final volume over the initial volume. We also saw earlier in the video that the ratio of heat or change in heat per unit temperature is the change in entropy. Okay. So let's start with the second expression here. So the change in entropy, if we wanted to sum over those changes, it would be the sum between final and initial conditions of the change in entropy. Or if we wanted to actually get, I guess, the overall change in entropy, we'd have to sum over the little differences. But because change in entropy now is proportional to change in heat, then it would just be the sum of the final and initial conditions of the change in heat per unit temperature. Okay, so using this expression here, we can work out that the overall entropy change that I'm considering, if I sum over the incremental changes between final conditions and initial conditions, and I can do that because entropy is a path function, and will give me a definite integral. Okay, so now I'm able to reconcile, essentially insert this Q, which is this material here, into this expression here. Okay, so we're going to take this Q and we're going to insert it right over here, which essentially says that delta S is the integral of Q over T. So I've got delta S is nRT over T log VF over VI this T will cancel that T, so we've got delta S is NR log VF over VI. This is one of the equations that it's important to know and you'll use at the general chemistry level. It's important to know that there's a positive sign here. There are other related equations that will have a negative sign here. And we'll come back to this equation shortly. The one thing I will point out is when you use R, because entropy has units proportional to joules, then it's important to use that 8.315 joule per mole Kelvin value rather than the other value that's more appropriate for atmospheric pressure type calculations. Okay. So continuing on, we've already looked at the effect of entropy and volume now. We're going to move on to the effect of entropy and temperature next. It's next on our to-do list. So we're going to recall an equation that typically you see in an introductory chemistry class, but it's also relevant at the general chemistry class level as well. So recall that heat is the mass, the specific heat, and the change in temperature, where I'll put a capital T. It really doesn't matter because it's a change in temperature, not an absolute temperature. But I don't want to confuse the situation with time, which typically has a lowercase t. So I'll go ahead and leave it with a capital T. So if you want to calculate heat, you've got mass, specific heat, and temperature change. Well, this implies that if we were to take the integral between final conditions and initial conditions of the change in heat, so here I'm assuming that the change in heat is equal to the heat itself, where again the line through the D just reminds us it's an indefinite integral, it's a path function. If we take that per unit temperature, remember from the previous slide, this is delta S. So this is a statement from the previous slide. Now, essentially, I've taken the left side and divided it by T. So this is going to equal mc delta T divided by T. Okay. So if you look here, I've got dq, which is just q, divided by T equals mc delta T divided by T. So this implies that the change in entropy, now notice that I'm summing over changes in heat. And heat here is proportional as the heat changes, the D. The only other term with a D is temperature. So the mass is a constant, the specific heat is a constant. Remember, specific heat is an intensive property. So I'm only summing over things that can change. Now you could, if you wanted to look at an incremental change, you could just replace the delta here with a D. So we would just have anything that's a constant that isn't affected by the sum, we could just bring to the left of the sum sign. So we could write MC and then write R sum between final and initial conditions. Because remember, the function sum only acts on anything to its right. It's going to ignore the mass and the specific heat. So what's left? I've got a 1 over temperature, which is this denominator here. And then the delta, I'm just going to write D. So it's a change in temperature, this function here. So we've seen this type of thing before when a sum hits 1 over an argument as the argument changes. So that's I guess, a template that you'd be good to remember. So the sum of 1 over a function as the function itself changes is just log base e of the function. So that's our aside. So I would recommend that you memorize that, which is exactly what we have here. So this implies that the change in entropy is just our constant mass times specific heat, and then we've got log temperature final over temperature initial. And this is an equation that's analogous to our equation for the change in volume. Now we've got a change in temperature, and instead of nr, we have mc. Notice also there's a positive sign here. So in our discussion of looking at entropy and volume, pressure and temperature changes, we've seen these two equations so far. We've seen a change in entropy is the product of moles, the ideal gas constant, and log final over initial volume. We've seen the change in entropy is the mass, the specific heat, multiplied by the log of the final over the initial temperature. Now we're going to look at the effect of pressure on entropy change. So we're going to start with this equation, and we're going to consider Boyle's law, which, remember, is the relationship between pressure and volume for an ideal gas, or at least we're going to consider the ideal gas situation. So Boyle's law tells us that the product of the initial pressure and the initial volume is equal to the final pressure and the final volume. Let's assume isothermal conditions. We're not going to worry about any adiabatic conditions, so we'll just assume that there's no exponent for volume. Well, if we pool like terms, so we'll put the volumes on one side of the equal and the pressures on the other side. Then we've got the final volume over the initial volume is the initial pressure over the final pressure. So notice the ratio here, final over initial, is reversed, initial over final for pressure. So ultimately, we're going to take this equation here with our final volume and initial volume, and we're going to replace it with initial and final pressure. So again, inserting this into this expression here, we've got change in entropy is nr log initial pressure over final pressure. Okay, we took this equation, this equality, and we put the right side of the equality into the parentheses here. Typically, this is not how the equation is presented. It's always nice to have final conditions as a numerator. So recall one of your log rules, that if we take the logarithm of a ratio a over b, we take the positive logarithm of that ratio. If we were to flip the ratio, we would just take the negative of that argument. So this is just one of the many logarithm rules that you need in early chemistry classes. So again, if you take the logarithm to any base of an argument, by taking the inverse argument, you change the sign of the logarithm. Well, that's exactly what has happened here. We've taken an argument, final over initial, but now we've flipped it, initial over final. So we need to rewrite this, but we're going to change the positive sign to a negative sign. So delta S is minus nR log final over initial pressure. So this is our third equation, and it's the only one with a negative sign here. So just to sum up, here are the three equations. It's always nice to see them next to each other. So you've got volume, temperature, and pressure. The only one with the negative sign is pressure, and it's because of the Boyle's law intervention, where the relationship between pressure and volume is an inverse relationship. So when we invert the fraction, we change the sign of the logarithm argument. So now we've looked at entropy changes under varying pressure, temperature, and volume conditions. Now we're going to shift towards looking at entropy as a driving force behind the phenomenon of mixing. So recall the equation we've just looked at. So the change in entropy is minus moles, the ideal gas constant, and then the logarithm of final pressure over initial pressure. So this is an equation we've just seen a couple of minutes ago. Now let's also recall Dalton's law of partial pressure. So Dalton here is the same John Dalton from Dalton's atomic theory. So Dalton's partial pressure so we have, let's say we have a gas A that contributes to a total gas. Then the pressure of the gas A, or the partial pressure of gas A, is the mole fraction of the component A out of the total pressure of the mixture. So this is the mole fraction of A in the mixture. This is the total pressure. And this is the partial pressure of A. So the piece is the fraction of the whole. That's how you'd interpret this diagram. Okay, so let's consider a mixture of two gases. So mixing and mixture, I want to clarify, mixing is a dynamic process where the two materials exchange location descriptions. Mixture doesn't imply mixing. Mixture just means there's more than one thing. A combination might have been a better word, but I'll stick with mixture. So consider a mixture of two gases, gas A and gas B. Well, this implies that the partial pressure of gas A is the mole fraction of gas A times by the total pressure, as stated earlier. And it also implies that the partial pressure of gas B is the mole fraction of gas B times by the total pressure. We can cross multiply and solve for the mole fraction. So this implies that the mole fraction of gas A is the partial pressure of gas A divided by the total pressure. So we just divide both sides of this equation by total pressure, and we get this expression here. And likewise, the mole fraction of gas B is the partial pressure of gas B divided by the total pressure. Again, we divide both sides of the top expression by total pressure. We get the bottom expression. Okay, I'm going to erase the board, tidy it up, and we'll continue looking at entropy of mixing. Okay, we just left off with statements that the partial pressure in a mixture of gases A and B, the mole fraction of that mixture that's A is the partial pressure of A divided by the total pressure of the mixture. And likewise, the mole fraction of the mixture that's B is the partial pressure of B divided by the total pressure of the mixture. Let's make some reasonable assertions. Let the entropy change, which we're arguing is the driving force of mixing, so the second law of thermodynamics, that push towards increasing entropy change of the universe, let's say that that a priori is the driving force of mixing. This is why things mix, and typically why they don't naturally unmix. So the mixing of A and B, let's say we have to consider the sum of conditions of A and B. So it would be the entropy change occurring for A. You know, is gas A obeying the second law of thermodynamics? It better. And then gas B. So the overall process, there's two constituents and they're both going to obey the second law, as they must. Well, this implies that delta S mixing well, I should probably state an equation ahead of time as well. Recall from the previous slide we had delta S for a gas is minus nR log P final over P initial. So that's one of our equations that we had previously. We're going to need that now. So for A, I'm going to sub in this equation for A, and then I'm also going to sub in this equation for B. So this is minus N of A, so moles of our gas A. R is just a constant, log the ratio of the partial pressure over the total pressure. Okay, so I've got my parenthesis here, and I'm assuming that my parenthesis is my mole fraction, or the piece that's relevant to A. And I'm going to add to that the second term, which is also negative. So minus NB R log mole fraction of B over the total pressure. Okay, so again, for the whole mixing process, I'm taking the sum of the individual terms, and I'm going to substitute in this term for each constituent gas in the mixture. So this implies that the entropy change of mixing, if I take both of these terms, and I can go ahead and factor out the constant R, so I can just say that equals negative R. So I've got a negative in this term, let's lump it in with the R. I've got a negative in this term, let's lump it in with the R, and let's factor that negative R out. Then I've got a mole fraction of A, log, and then this expression here we know is the mole fraction of A. So log the mole fraction of A. And then I've got the mole fraction of B. Sorry, not mole fraction, moles of B. N is moles, X is mole fraction. Moles of B, log, and then this parenthetical term here is the mole fraction of B. Okay, and let's call this expression A. So let's call this expression A. Notice at this stage that entropy of mixing is always going to be a positive value. So it obeys the second law of thermodynamics. Why? Because mole fractions are always less than 1. And when you log anything less than 1, you get a negative value. That negative value is going to hit that negative and make the whole thing a positive value. So we're in total compliance with a second law of thermodynamics. So let's call that equation A. I'm going to tidy up the board and we're going to produce an equation B, and then once we have equation B, we're going to combine them together. Okay, so we're going to continue. We've just seen equation A. Recall another way to phrase the second law of thermodynamics is that the change in Gibbs free energy is the sum of enthalpy conditions and entropy conditions. So this is a statement of the second law. Change in Gibbs free energy is the enthalpy change minus temperature multiplied by the change in entropy. This negative here, I would consider it just a positive, just adding a negative term. So it's the energy and the entropy conditions added together, the sum total of those conditions. So remember, we're keeping the second law firmly in our rear view mirror, keeping it in our mind. Well, this would imply that the Gibbs free energy of mixing is the enthalpy of mixing minus temperature multiplied by the entropy of mixing. And we already know this one. We have an expression for this. Recall also that minus change in Gibbs free energy per unit temperature is change in entropy. So we've seen this previously in a previous video, so we're just going to state it again for now. We can turn the D's into deltas to make people feel more comfortable. So we can write delta G over T is delta S. We can, if we want to solve for a positive delta G, we can take that negative and put it over here. And we already know this value, so we can just rewrite it, but change the sign of it and multiply it by T. So this implies that delta G mixing is minus delta S mixing over temperature. So we just solve for delta G here and put the label mixing on. So this implies that delta G mixing is minus delta S mixing. So we lose that negative sign and it just becomes positive R. And we also have temperature now. And then we have mole fraction, moles of A, not mole fraction, mole of A log mole fraction of A plus moles of B log mole fraction of B. Let's call this equation B. Okay, so we have this expression here. I just want to double check that we're comfortable where this came from. Just want to recap the delta S mixing. We said that the delta S mixing was negative R moles of A log mole fraction of A, and moles of B log mole fraction of B. We call that equation A. So I just want to recap that with everyone to make sure that there's not an issue. So to go from the entropy of mixing, which was this expression here, we took this equation here, and essentially we have to get rid of the negative, or rather, I guess probably the easiest way to think of this is to look here, right? So if you look over here, we've got delta G over T is minus delta S. So if we transpose the delta T multiplied by both sides, we get delta G is, oops. All right, so that T shouldn't be there, because I've got delta G, that T should be up here, right? So that was a mistake. So that T should be over here. Okay, so delta G mixing is negative T delta S. So if we take our delta S mixing, we lose the negative because we've got a negative that impacts this negative to make it a positive. We've got the delta S mix, which is all of that stuff, and we've got T, which now appears as a T. Okay, so I've just caught a little typo I did. So this is now the correct equation that we should have used, which hopefully you would have spotted before I did. Okay, I'll clean the board up one more time and we'll finalize this expression. So just to recap all on one board, we've got an expression for the entropy of mixing, which was this expression. It's negative. So we call that equation A. We've got this expression, which is positive, and there's a temperature, which we call expression B. And we recall our canonical statement of the second law, which looks at Gibbs free energy being the sum of enthalpy considerations and entropy considerations. So this would imply that the enthalpy of mixing, which is the only one we don't have now, is just going to be the Gibbs free energy of mixing. If we take the T delta S term over here, plus T delta S mixing. Okay, so we're just going to sum these two expressions together. So delta H mixing is delta G mixing, so which is RT NA log XA plus NB log XB. So it's essentially equation B plus T delta S. So that's T, and then all of this, well, I've got minus R. Let's make that. So I've got minus T and R. And then I've got NA log XA plus NB log XB. So as you can see, I've got the expression in the parentheses is identical to the expression in the parentheses. And then the multiplier, positive RT and negative RT. So these two expressions are exactly equal, but with the opposite signs. So we've just learned that the enthalpy of mixing is exactly 0. So we've just learned that mixing, natural mixing, has got nothing to do with the energy of the system. so long as we don't extraneously change the energy, it's naturally an entropy-driven process. So we can conclude that mixing is not naturally an energy-driven process. Mixing is an entropy-driven process. Finally, just to drive home something important that we're going to see moving forward into electrochemistry, that a positive change in entropy is a sign that the second law is being obeyed. But we saw that this change is proportional to the opposite sign of Gibbs free energy. This symbol means proportional to, so evidence that the second law is being obeyed, we can see that as a positive entropy change or a negative Gibbs free energy change. And that's something that's going to be important moving forward. So this will conclude our short video on entropy considerations with temperature, volume, and pressure, and latterly entropy of mixing as the mixing process is an entropy-driven phenomenon.